Have you ever really stopped to think about how your ideas, your clicks, your commands actually make a computer do something? It's not magic, not at all. It's language. But, it's a language built on a completely different kind of logic. And getting your head around it, well, that reveals what a machine truly is. So let's break it down. So how do we actually bridge that gap between us and them? I mean, you can't just talk to a computer like you would a person. You need a special kind of language, one of pure instruction, where every single word is a precise, unambiguous command. We literally had to invent a way to speak machine. At its core, what we're sending the machine is a computer program. Think of it like a recipe, but one that's so precise. These instructions are the intangible part, the software, the ideas that take control of the tangible, physical parts of the computer. Your keyboard, the processor, the screen right in front of you. Now, to create these special languages, the pioneers of computing did something pretty clever. They looked at a system they already knew inside and out, human language. They built the entire foundation of programming by kind of mimicking the grammatical structure we all use every single day. And the parallel is actually incredibly direct. In grammar class, right, a noun is a thing, a person, a place, some kind of data. Well, in programming, we call that an operand. A verb is an action, and in programming, that's the operator. That's the symbol, like a plus or minus sign that actually does something to the data. See? It's the same core logic. You've got a thing, and you've got an action. And this chart just illustrates that evolution perfectly. Spoken speech combines an actor with an action. Written language formalizes that into a sentence with a noun and a verb. And then, programming language distills it even further into a computer instruction, which combines data, the operand, with an action, the operator. It's the same fundamental structure, just tweaked for a totally new purpose. But, and this is a really big but, we have to be careful here. While that metaphor is a brilliant starting point, it's the differences between human language and programming language that truly define how code works. Okay, take a look at this famous little line of code. You'll see this thing in countless programs. Now, if you read this like it's a math equation, it makes absolutely zero sense. I mean, how can a number be equal to itself plus 1? The answer is no, because this isn't math. That equal sign doesn't mean is equivalent to. In programming, it means gets. This isn't a statement of truth. It's a command. It's telling the computer, hey, take the value you have stored in memory location I, add 1 to it, and then put that new result right back into I. It's all action. And this right here reveals some really fundamental divides. Human language is for other people. Code is for machines. And because of that, a computer never learns a language like we do. It just mechanically executes signals, pulses of electricity. We process abstract meaning. It processes physical stuff. And that's why a computer can be programmed to find a typo, a syntax error, but it has absolutely zero understanding of what that mistake actually means. That tool for checking all the errors, well, that's called a compiler. You can just think of it as a ruthlessly strict grammar checker for code. It makes sure every single instruction follows the language's rigid rules before it ever gets near the processor. So for a person, for you or me, to get familiar with one of these languages, it's a very disciplined process. It's not like picking up slang. You have to learn the specific alphabet of symbols, then learn how to build valid strings and instructions, and then combine them into complex programs, all while following super strict standards. It really just takes a lot of practice. All of this, the precision, the rigid rules, the focus on pure instruction, it all makes perfect sense when you just take a step back and remember what a computer actually is at its most basic level. First things first, a computer's job begins by accepting input. And that's not just data, like the words you type. It's also the instructions for what to do with that data. Every single click, every keystroke, that's all input. Second, it processes that input. This is the thinking part, where the hardware inside just mechanically follows that recipe it was given. This is where a command like I equals I plus 1 is actually executed by the processor's logic gates. And third, after all that, it produces an output. Once the processing is done, the result is delivered in the exact format the instructions specified, whether that's pixels lighting up on your screen, sound coming out of your speakers, or a document getting sent to your printer. So, putting it all together, here's the formal definition. A computer is simply a device built to do those 3 steps: accept input, process it with instructions, and produce output. Everything a computer does, I don't care how complex it seems, it all boils down to that simple loop. Input, process, output. So why is this specific way of talking to a machine so important? Why does this whole idea of a programming language matter so much? Because it's the secret ingredient. It's the whole reason a modern computer is so different from every other machine ever invented. Think about it. A calculator can only calculate. A car can only drive. But a computer can do almost anything because we can give it brand new instructions, a new program, at any time. At the end of the day, that's the real power we're looking at here. A programming language is the essential bridge, the translator that lets us take an abstract idea from our own minds and command a physical machine to make it real. It's an unbelievably powerful tool, which leaves us with a final thought. Since code is the language we use to instruct our machines, what are we going to command them to build, or maybe even to say next?